All right, ladies and gentlemen, so today here we're going to start off Chapter 3. Chapter 3 is polynomial functions. We're just taking a bit of an introduction to polynomial functions today. We'll take a little bit more of a deep dive tomorrow. First, I'd like to connect it to what you have studied before. So in grade 9, I know you focused on linear functions. Most of grade 9 is focused on linear functions. That's y equals mx plus b. That's calculating and estimating slopes, right? That you're first introduced to a slope in grade 9. Now your base linear function, we know what that looks like. That looks something like this. For example, that might show up as y equals x, right? Your base linear function is y equals x. We can apply certain transformations. We know how to do that now. Now, in grade 10, you moved on beyond linear functions. You started working on quadratic functions, and that is y equals x squared. It's your base quadratic function. Again, this should be extreme review for you. Looks something like this. In grade 11, you learned a few new functions, one of which was your cubic function, right? Your cubic function, that is y equals x cubed. I'm sure you see the pattern where I'm going here. Your cubic function looks, something like, something like this. Right, now each of these functions are examples of power functions. Now a power function is set up in a way that you have seen before, where you have a coefficient. In this case, we used a. It can be any number that's part of the real numbers, and it has a variable where it has here your independent variable. Your independent variable, obviously, we're used to using x here, and lastly, it has an exponent. Right now, you might say, well, there's not really an exponent on my linear function y equals x. Yes, there is. There's a hidden exponent of 1. Right, so a power function will look like this. It'll be made up of a coefficient, a variable, and an exponent. Of those, if there's no exponent like this, then we know there's an exponent 1. If there's no coefficient, let's say we're just working with y equals x, right? There's no coefficient to be seen here. Well, there is a hidden coefficient that's also 1, right? This is 1 times x. Right, so we do have a few hidden pieces in what we're working on here, but each of these make up our power functions, and we're going to use these power functions to create our polynomials in here today. Right, so that we call them power functions. Now, the exponents that we're working with here in a power function, there are some rules to it. It must be made up of natural numbers, right? So your exponent, if it is a natural number, that means it is a counting number. So that means it is the number 1, 2, 3, 4, 5, and really will allow as well, I guess the whole numbers here will allow 0. We can have an exponent of 0. What does an exponent of 0 do? If we remember our exponent rules, if we have x to the power of 0, anything to the power of 0, that just equals 1. Now, we can use these, like I said, these power functions to create polynomials. A polynomial function is a sum, meaning adding, right? Or a difference, meaning subtracting, of power functions. Okay, well, that's great. We now know what makes up a power function. So we could add some together or subtract some from one another in order to create a polynomial. A degree of a polynomial, we call it the degree. A degree of a polynomial function is the highest exponent on a variable in the function. We need to be careful there because let's say we have a polynomial y equals 3 to the power of 4 times x. And you know what, let's be a little bit nicer to us. 2 to the power of 4 times x to the power of 3. There are two exponents in here, but only one exponent has a variable in its base. So the 3 has a variable in its base. This is akin to writing 2 to the power of 4, that is 2 times 2 times 2 times 2, that's 16 times x cubed, right? And we can see right away the only exponent of note, the one we care about, is that 3. So that's why we say the highest exponent on a variable in the function. Now, we name our polynomials according to their degrees. Okay, so if there's a degree 0, we call it a constant function. An example of a constant function, y equals 4. Right, a constant function y equals 4, that would be a horizontal line across at the height y equals 4, right? That's just one example of a constant function, obviously. Our linear function, again, you've seen that term before, a quadratic, a cubic. If the degree is 4, we have a quartic function. If the degree is 5, we have a quintic function, etc. We can have a the names will continue for a long time, but we don't necessarily need to memorize these names. We don't need to know all of these names as they go on. You should be familiar with a linear, a quadratic, a cubic, and probably a quartic. You will get more used to these prefixes, but either way, we can call them nth degree polynomials, in which case we would say here, a quintic function, we would call a 5th degree polynomial. Right, so we're nth here, n is the degree. Okay, now from our previous math courses, you should have learned this before, so we're going to go over them pretty quickly. Even if you've learned them before, you probably did not spend too long on your finite differences, other than in grade 9 when you were just exploring linear functions. Other than that, I know you used them in grade 10, but I suspect many of you will not remember them, and that's okay. So your finite differences are differences between consecutive values in a table. Now, this is a pretty rough definition. Another requirement is that our table of values must have a consistent difference between consecutive x values. So in this case, each x value is increasing by 1 above the x value beforehand. So we're building our table in a certain way, and then we can take the differences between consecutive values in this table. Okay, so that means if we're considering the finite differences, what we're considering here, the finite differences, we're taking them from a pair of points, if you will. So here we would say, okay, so the first finite difference would be 15 minus 18. Okay, so this is y2 minus y1. I know you've seen this elsewhere in the course, right? y2 minus y1, that is 18 minus 15, and that equals, sorry, that's 15 minus 18 rather. Negative 3. So our first finite difference, which we call delta x, right, is negative 3. We can see our next finite difference would be 12 minus 15. That is, again, negative 3. Our next finite difference, 9 minus 12, that's negative 3. And our next finite difference, 6 minus 9, negative 3. We cannot calculate a finite difference down here because we need 2 y values to calculate a finite difference. Now we notice, obviously, because this is a linear function, then our first finite differences that we calculated are all constant. That's what tells us it's a linear function, right? Again, this should be reviewed. Then, looking forward at a quadratic function. Again, these are data points for a quadratic function. With a quadratic function, I've already calculated your first finite differences here. Next, we'll look at the second finite differences. So we'll take these finite differences and we'll subtract these. So that is, it's our finite difference. How should I write this? Delta f1, or sorry, f2 at x minus delta f1 of x. Okay, so we're setting it up in the same way here. The difference is our inputs are our first differences. Right, so here we take 16 minus 12, and I know what 16 minus 12 is, that's 4, right? 20 minus 16, our next finite differences are 4. 24 minus 4, our next finite differences are 4. So again, you'll notice that we've come across some constant finite differences. This time, though, it was our second finite differences, right? Our first finite differences were different. Our second finite differences were constant. So with a quadratic function, our second finite differences are constant. We notice a bit of a pattern here. Linear function, first finite differences are constant. Quadratic function, second finite differences are constant. So all polynomials, every single polynomial function will have a constant finite difference. The number that is constant, so if it's your first finite differences, that means your degree is 1. So the number of the constant finite differences tells us which degree we're working with here. So again, that is our degree equals 1 here, and that is a linear function, right? Our degree equals 2 since our second finite differences are constant here. So we could find our degree from the equation by determining the highest exponent on a variable, or we can find the degree from a table of values by determining which finite differences are going to be constant for us. Okay, again, much of this is review. Some of this you've learned before, but you've likely forgotten. We'll keep pushing forward. This should still be a nice short video for us. We'll just do one example here today. So example 1, we'll take a look in here. We have a function like this. You actually should recognize the form of this here, which could tell you what to expect. But either way, we're going to take a look and see if this is a polynomial. Well, we need to be careful, right? We were already told how to recognize the equation of a polynomial. We'll go way back up here. A polynomial is made up of a sum or difference of power functions. We have our power functions all right here. Right? Well, a sum or difference of power functions typically might look like f at x. It might look like 5x cubed plus 2x to the power of 2 minus 17x to the power of 15, right? Where we're building each term in the same way with a coefficient, a variable, and a degree. A coefficient, a variable, and then a degree. A coefficient, a variable, and then a degree. That's not how this one looks, right? So right off the start, I might say, well, this doesn't really look like a polynomial, but we know a little bit better than that, right? We should be able to recognize this from grade 10 or grade 11 as a quadratic x-intercept form, in root form, right? So here, what we want to do, in factored form rather, what we want to do is we want to say, okay, well, how can I get this here that I know is supposed to be a polynomial to look like that? Well, what I can do, and again, you should see where I'm going, hopefully. If not, then I am walking you through it. You can distribute here, right? We can use our FOIL. So 3x times 2x, that's 6x squared. 3x times negative 9, that is negative 27x plus 2x minus 9. Okay, where all of a sudden, right here, even before I simplify it any further, I recognize this in the form of a polynomial. This is a sum or difference of power functions. Sum, difference of power functions. Therefore, it is a polynomial. Now, we can get a little bit, so really what we can conclude from here is that a product of polynomials, okay, and maybe we're jumping ahead by concluding it, but I'm hoping you can see at least this is one example where a product of polynomials will also be a polynomial, right, because of how our distributive property works. Okay, I'm rather than writing that, we don't need to. You don't need a video of me saying that. A product of polynomials will still be a polynomial, where product is the result of a multiplication problem. Now we do need to. You know what? We'll go into greater detail there later. You should be able to handle something like this. This is a bit of an exploration on your own. I have the shape and end behaviors of polynomials written down here, where we have degrees, polynomial of degree 0, degree 1, 2, degree 3, 4, and 5. And I want you to compare their domains and see if there's any pattern, see if there's any consistency. I want you to compare their ranges, again, see if there's any consistency. I want you to compare their end behaviors, see if there's any consistency, and then continuity and asymptotes as well. We'll talk about our conclusions when we're in class for 3.1.